In order to solve any problem in computer science, generally we write programs. Before writing the program in any programming language, it is always better that we write an informal description of the solution, which is also called as algorithm. Okay, so see, now we have some problem to solve in computer science, and generally we solve the problems by writing programs, right? So if you have to directly write a program in some programming language like C, before writing the program you should write a blueprint, right? Or a, what can we say, in an informal language. In English like language, we want to describe what we want to write so that it will be easier for us to communicate before implementation. Okay, so that is called algorithm. So before going for any problem, solving problem, we have to write a program, and for writing a program we need algorithm. In general, if there is a problem P1, then there might be many solutions, right? So each one, let me call each solution as an algorithm. So there may be many algorithms, A1, A2, A3, A4, so on. There will be many solutions. Now, before implementing any algorithm as a program, we have to find out which among these algorithms are good in terms of time and memory. So we want to analyze every algorithm in terms of, one is time. Time means which one could execute faster, and second is memory. Memory means which one will take less memory, less time and less memory. So the course Design and Analysis of Algorithms, Design and Analysis of Algorithms will talk about how to design various algorithms, like for a given problem how many algorithms are there and how to analyze them. So what will be the time taken by each one and what will be the memory required by each one. After designing and analyzing, we shall take the best algorithm. Let us say if this time taken by this one is something and time taken by all of this one is taking the least time and least memory, then we shall implement it as a program in C. So that is what is the main purpose of design and analysis of algorithms, right? So before going into taking an algorithm and analyzing it, we should get familiar with the terminology used in algorithms. So some of the notations which are used in algorithms are these. One is they are called asymptotic notations. Okay, so first one is big O. Big O represented like this, okay, by capital O. So big O is nothing but, if you found out that, let us say you have found out that the algorithm, as the input size is increasing, if the time is increasing like this, okay, so this is the time complexity or the rate of growth of time, and this is the time growth, this is the n, which means if I keep on giving larger inputs to the problem, if the time increasing is like this, let us call it f of n, where f is a function of n and n is the size of the input. Assume that the time is going to increase like this as the input is increasing like this. Then what is the worst case or upper bound for this function? So we'll find out another function in such a way that that function is greater than the given f of n. Let's call it c into g of n after some limit n equal to n naught. Okay, so for a given function, how do you find out f of n? I'll tell you later. Given an algorithm, you should be able to find out what is its time complexity or what is its f of n in terms of input n. Now if you, after finding out this, if you can bound that function by some other function c into g of n in such a way that after some input n naught, the value of c into g of n is always greater than f of n, which means if f of n is less than or equal to c into g of n after some n greater than or equal to n naught, after all the values of input greater than or equal to n naught, where c comma n are real numbers and c is greater than 1, sorry, c is greater than 0 and n naught is greater than or equal to 1. For these conditions, if you satisfy this equation, then we can say that f of n is big O of g of n, which is nothing but f of n is smaller than g of n. That is what we could say. Okay. So I'll give you some few examples and find out if f of n, if these conditions can be met. So see this. Let us say f of n equal to 3n plus 2 and g of n equal to n. So can we say that f of n is big O of g of n? If we have to say this, we have to find the two constants c and n naught. So if this has to be followed, then what should follow? F of n should be less than or equal to c into g of n for some c greater than 0 and for some n naught greater than or equal to 1, for some n greater than or equal to 1. Now what is f of n? 3n plus 2 should be less than or equal to c into n. Okay. Now when can 3n plus 2 be less than or equal to cn? So you can substitute any value for c. So the best option is, by looking at this, I found out that c when it is equal to 4, that is better. Anything above 3 is also good, right? If I substitute c equal to 4, what I get is 3n plus n is less than or equal to 4n. Yes, we found a c. And what about n? So if you substitute, if you bring this 3n this side, then n has to be greater than or equal to 2, which means for every n greater than or equal to 2 at c equal to 4, f of n is less than or equal to c into g of n. Therefore 3n plus 2 is equal to is big O of g of n. Now we found out that if f of n equal to 3n plus 2 and g of n equal to n, then we found out that f of n is big O of g of n, which means this 3n plus 2 can be written by a constant multiplied by n, and therefore cn plus 2 will be less than that. So if n is bounding this function, definitely n square will bound, which means if g of n for this one it is satisfying, then for any value greater than n, which means g of n equal to n square or n cube or n power n or 2 power n, for anything, all these functions are going to bound 3n plus 2. But we have to keep in mind that always big O is upper bound. Definitely, any of these answers is right, but always go for the least upper bound or the tightest bound. Here the tightest bound is n, right? So any of the answer is fine, but then go for n. Okay. Next one is big omega. Okay. So we generally write it as big omega of n. Let us say the actual time complexity or the function which is determining the time for an algorithm is increasing like this. So you have something increasing like this, and now you want to give a lower bound for this. Let us say this is f of n, which is n is nothing but the number of inputs. As the inputs are increasing, as the size of the input is increasing, the function is like this for some algorithm. And now if I give a lower bound for this, let us say this is c into g of n in such a way that c into g of n is less than f of n after some value of n, which is n naught, which means f of n is greater than or equal to c into g of n after some value of n is greater than or equal to n naught, where c is a constant which is greater than 0 and n naught is some input which has to be greater than or equal to 1. Why n naught is always greater than or equal to 1 is it is input has to be at least 1. Okay. Now let's take an example and I'll explain you how it is going to work. Let us say f of n equal to f of n equal to 3n plus 2 and g of n equal to n. So can this f of n be bounded by g of n, which means can this f of n has lower bound as g of n? Just check this. So if that condition has to happen, if f of n has to be big omega of g of n, okay, then f of n should be greater than or equal to c into g of n. So what is it? F of n is 3n plus 2 has to be greater than or equal to n. Obviously 3n plus 2 is greater than or equal to c into g of n, even if c equal to 1, right? So even for c equal to 1 this is true, and moreover for what values of n? All values of n. Therefore n naught is greater than or equal to 1. So c equal to 1 and n naught is greater than or equal to 1. We found out the values of c and n for which the condition gets satisfied. Therefore we can say that 3n plus 2 is omega of n. Okay. Now is this 3n plus 2 is omega of n means 3n plus 2 will be lower bounded by n. So can we check if 3n plus 2 and n square, let us say f of n equal to 3n plus 1, 3n plus 2 and g of n equal to n square. Can 3n plus 2 be lower bounded by n square? Just check this. If it has to be 3n plus 2 has to be omega of n square, which means if we don't know, right? So if 3n plus 2 has to be omega of n square, we are not sure, that is why I am writing with a question mark. Then what should happen is 3n plus 2 has to be greater than or equal to c into n square for some n naught, for some value of n naught, which means after some value of n, given some values of n, this condition should satisfy always after n naught. Then can you find such as c? It turns out that we cannot find such as c for which this condition can be satisfied, which means 3n plus 2 can never be lower bounded by n square, but then it can be upper bounded by n square. Okay, so if you found out that f of n is omega of n, then anything less than n can be answer, which means if f of n is lower bounded by n, then it will be even lower bounded by anything less than n, which means you can go for log n. Log n is less than n, it will be lower bounded by this, or you can go for log n, it will be lower bounded by this. Okay, so what I mean to say is there will be more than one answer for big O and omega always, but then it is better that you take the closest bound or the tightest bound, tightest lower bound here, and in case of big O, tightest upper bound. Okay, we shall see more examples about it. Now let's see theta. Big theta. Okay, so what about big theta is, if I have a function f which is growing with respect to n, if this is the size of the input, and if a function f is there which is growing with respect to n, okay, then I should find both the upper bound and lower bound by a function just by varying the c values of constant. So if I can find a function which can even upper bound it and lower bound it, if this is f of n and this is c1 into g of n and this is c2 into g of n, if f of n is bounded by g of c1 into g of n and c2 into g of n, then we can say that f of n is theta of g of n. So these constants c1 and c2 could be different, and moreover after what value you could take any value after which it is true. So let us say this value is n naught, which means after this value of n naught both of them will agree, which means c1 into g of n will be less than f of n and c2 into g of n will be greater than f of n. Okay, so we say that a function f of n is theta of g of n if f of n is bounded by g of n both in the lower as well as upper, right? So which means C1 into G of n should be less than or equal to f of n should be less than or equal to C2 into G of n, where C1 and C2 are constants greater than 0, and this should be valid for all values of n naught greater than or equal to some. For all values of n greater than or equal to n naught, where n naught has to be greater than or equal to 1, any constant. N naught can be any constant, right? So in the previous example, if you see, once we have taken this example, so f of n equal to 3n plus 2 and g of n equal to n, right? And we have seen that f of n is less than or equal to g of n, f of n is less than or equal to c into g of n, where c equal to 4. If I have this 3n plus 2, it is less than or equal to 4 into n, where c2 equal to 4, which means I can find out the upper bound for the function f of n when I substitute in place of c2 4, right? And this is valid for all n naught greater than or equal to 1. This is valid, isn't it? So always 3n plus 2 is less than or equal to 4n, which means g of n can be a upper bound for f of n, as well as let us see if it is lower bound as well. So f of n is greater than or equal to c into g of n for what values? 3n plus 2 is greater than or equal to, let us say this is c2, this is c1, okay? And now if I substitute c1 is equal to 1, which means c1 equal to 1 means I get n. Then for all values of n naught greater than or equal to 1, then I can say that f of n is greater than or equal to c1 into g of n, which means this 3n plus 2 is bounded by g of n both in the upper bound as well as lower bound. For the upper bound, c2 is equal to 4, and for the lower bound, c1 equal to 1, and both the cases are valid for n naught greater than or equal to 0. So sometimes this theta is also called as asymptotically equal, which means if the leading term in the function is going to be n, then you can take n as the g of n because they are asymptotically equal. If I have 3n square plus n plus 1, then it will be theta of n square, isn't it? Always the leading term, the dominating term can be taken here. If I have 3n cube plus n square, this is always theta of n cube, okay? So now we have seen three notations. I'll show you why these three notations are useful: big O and big omega and big theta. Okay. So we have seen what is big O and what is omega and what is theta. Then what are the practical significance of all these notations is, given any algorithm, big O is going to say the worst case time or the upper bound, which means if you are giving any time in terms of big O, it is also saying that in any case your time will not exceed this. So if you are giving the time in case of if you are using omega, it is giving the best case, which means in any case you can never achieve better than this, and theta is giving you the average case, right? So generally this omega gives us the worst case, okay, and big O gives the worst case and omega gives the best case and theta gives the average case, right? So if you see, in practice, we are not interested in what is the best time that this algorithm could execute. We are always interested in what is the worst case time that will be taken by this algorithm for any input. That is what we are interested in. So we are not interested in finding out the best cases. We are generally interested in finding out the worst case, right? And when do we use this average cases? When best case and worst case both are same. For some algorithms, the best case and the worst case both will be same, which means there is, for any input, it will take the same time. So in such cases, generally we go for theta. Understand this? So in practice, we are going to use big O in the worst case time to find out the worst case of an algorithm, and we are going to use omega in order to say that this is the least time possible. You can never go beyond that, which means it is the lower bound, it is the upper bound, and it is the average case. So in order to make this point even clear, I will take a practical algorithm and I will show you how it works. Assume that we have an array of numbers like this: 5, 7, 1, 2, 4, 10, 20 and 11, something like this, an array. Now we have to search for an element. So given this input, let us assume that the size of this array is n. Let us say I want to search for an element. Then in best case, and I'm going to use linear search. Linear search means I'll compare. Let us say x is given and I want to find out whether this number x is in the array or not. Then I'll take the x and compare with the first element, second element, third element, fourth element. I'm going to do this sequential search, okay, linear search, which means I'm going to not go to any particular element. I'll go to all elements one after the other. So given this algorithm, what is the best case time we could execute this algorithm in? So best case time is nothing but if the element that we want to search is 5, then in best case we could search it in one comparison, isn't it? Which means in just one step we can find it out. Therefore the best case algorithm, best case time, if you want to write, you have to write like this, omega of 1, which means in best case you can find out the element in just one comparison or in one step. Now then, what is the worst case? Worst case is if I have n elements in the array and if I am searching for an element, then in worst case I might have to compare with all the elements. Therefore worst case time is going to be big O of n. Then what is the average case? Average case is worst case, and in general, if there are n elements, if you do some amortized analysis is nothing but average analysis. So you can find out that it is nothing but theta is big, theta of n by 2. So which is nothing but theta of n. So that is how all these three notations are varying. So first notation says that this is the worst case, you can never go beyond this. And this notation says that this is the best case, you can never go down beyond this, you can never go up beyond this. And this is generally average case is used whenever worst case and best case are same. So for this example, we don't generally use average case theta, right? So we are going to generally, for any practical purposes, we are never interested in best case, we are always interested in big O. And in case best case and worst case both are same, we generally use theta. So keep that in mind. Okay.